today we'll see first the topic of angles. Okay, so take a look. One of the important pieces of theory you need to remember is this property or theorem that is called exterior angle. Take a look at the picture. In the picture, you can see a triangle. And what is the concept of interior and exterior angle in a polygon? A triangle is also a polygon. Well, an interior angle is this, for example, also this and this, okay? In any polygon, in any of the vertices of the polygon, an interior angle is formed. What do we call an exterior angle? Well, an exterior angle will be the angle that is formed on the vertex of a polygon when you prolong one of the sides, okay? The prolongation of one of the sides in that vertex with the other side converging on that vertex, okay, these two form this angle here. And as you can see, this angle is supplementary to the corresponding interior angle in that very vertex. So that is what we call an exterior angle in a triangle. In this vertex indicated here, the interior angle would have a measure of c degrees. The exterior angle would have a measure of x degrees. Okay. Here we can also define an exterior angle. For example, if we prolong this side of the triangle, okay, here there would be one exterior angle that we can call y. And of course, also here, if we prolong this side, okay, we have an exterior angle z. So what can we say about exterior angles? They are always supplementary to the corresponding interior angles in the corresponding vertices where we are drawing them. So the exterior angle theorem says, for the case of a triangle particularly, that at any of the vertices of a triangle, if you draw the exterior angle will have a measure that equals the sum of the other two interior angles in the same triangle. So here you see the measure of this angle x will be a plus b. That is the sum of this and the sum of this. And it makes sense, right? Why? Because we know that because they form together a flat angle, that is a 180-degree angle, x plus c must be 180. On the contrary, or on the other hand, the three interior angles of any triangle will always add up to 180 degrees as well. So what happens if we do a match in these two equalities? Clearly, the measure of this is the same as the measure of this. So it's no wonder, okay, this theorem is nothing strange really. So this is something that reminds us that when we look in a problem about triangles, we look at triangle, always be careful, not only look at the interior angles but also at the possible exterior angles on the vertices of this triangle. Let's see an example of this and a sample question in the SAT. Take a look. We see the figure and we can see clearly there is like a line segment from A to B, and on top of this segment, coinciding, with one of the sides of a triangle CDE, okay, we have several angles in the figure and we need to determine what's the value of X in the figure above. How could we calculate X? Okay, where do we see X? We see X here. And also it appears here as part of this angle, right? 3x. Okay, so, okay, Madeleine, good calculation. Let's see how we calculate this. So first we are saying that in this triangle, the exterior angles comply with the exterior angle theorem. So you can take a look at this, for example, and say that 3x as an exterior angle DEB, right? That's a measure of the exterior angle DEB is equals 3x. Okay, that angle should be the sum of this and this, right? The sum of the other two interior angles in the same triangle. So here, what would be this angle here? Well, that's easy, right? Yeah, because we can see that if this exterior angle is 100, obviously this has to be 80 because the sum of the two form a flat angle of 180 degrees. So now we can formulate an equation. We can say 3x must be equal to x plus 80. And of course, from this, you can easily isolate x, which would be 40 degrees, right? We're working with degrees. That's it. All right, so let's now see some more properties of triangles. Okay. Well, actually, we're not dealing with triangles in this very moment. We'll see more properties about triangles later on. But what we said a moment ago about, the exterior angle property, this applies basically on triangles, okay? Okay, what happens with parallel lines when they are intersected by a third line that is not parallel to them? Well, this idea you know well, right? This theory of, alternate angles. When two parallel lines cross a third line, then the same set of four angles are created around the intersection points. So here we have that this angle here is opposite to this one, so they are the same. This is also the same as this one. But the same four angles are created here. So this creates the sensation that the triangles can translate or can be moved and the corresponding measures coincide. So this angle labeled as angle 3 has to be the same as angle labeled 7 and so on, okay? So using this basic set of matching angles, we can see questions like this. Take a look. Okay, there's like a little convoluted figure, triangle inside triangles. They tell you that in this figure, segment AC, that is this, is parallel to GD, so parallel to this. And at the same time, BF, this, is parallel to CE. And we have some angles measures. So what's the value of X? Okay, I'll leave you to try and calculate this one. Okay, and as you try to solve this one, please allow me a little interruption. I'll get a glass of water, please. Okay. So how do we do this? So here, actually, there are several sets of parallel lines or line segments in which we can apply the property that we just mentioned, all right? So that's what we'll do. Okay, so here, please take a look at this. First of all, if you just consider what would happen if you consider the lines marked in blue, okay? The lines marked in blue. So these two lines you can consider that are intersected by the same, for example, the same line, which could be this, perhaps. Let me signal that in blue here, this one. You can consider that segments AC and, you know, AC and CGD can actually be intersected like by BF and also CE. Okay, consider what happens here. Since these two segments are intersected by this one here, by CE. So wouldn't it be true that this angle here is the same as this? This has to be 40. They are in an equivalent position, right? Okay, so, but now consider what happens in the two lines or line segments signal in red. DE and BF, or CE and BF. We can consider that these two, this and this, are intersected at the same time, since they are parallel, by the segment DG. They are intersected by DG. So this angle here is in the corresponding position of this angle here. So this has to be 40 as well. And then now, observe what happens if the two segments in blue, you consider that they are intersected at the same time. That is, this and this are intersected at the same time by this. So this angle 70 has to be the same as this one here. And that's it. So if in the small triangle, let's define the name of this point, let's call it P, the crossing point here. So what happens in triangle PGF? In triangle PGF, angle X is an exterior angle. And by the theorem of the exterior angle, this measure here has to be the sum of the two interior angles in the same triangle. So it would be this angle plus this angle. So 40 plus 70, this is the sum and the answer to the question, 110. So you two did well, Luciana and Madeleine. Good answer. Okay, so the idea is not to get lost in, the diagrams that could be a little convoluted, a little complex. The idea is in isolate pairs of segments and observe where there are opportunities to apply the property, okay, of parallel lines. Let's see some more examples. And now, as we move on, when we talk about angles, there is an important property that we need to keep in mind. When we have polygons, that is closed figures formed by different line segments connected at their vertices or their endpoints, right? As you can see here, we have a closed figure formed by three line segments. So we call them sides, and these endpoints, these joints, we call them vertices, right? These are sides, and this is called a vertex. Vertices in plural. All right, so how do we determine the sum of all their interior angles? There is a formula here. If you try this formula, introducing the number of sides of the polygon, then you get very easily what is the total sum. This formula comes from the fact that if you, for example, draw from one vertex of a polygon several diagonals, that is segments connecting that vertex with opposite vertices in the same figure. For example, here you can connect this with this and with this. What can you appreciate here? Well, it's really easy to see that by drawing these two diagonals, we have divided the pentagon in three triangles. But there is like a universal truth about triangles. In any triangles, the three angles, interior angles, let's call them alpha, beta, and gamma. What is one important fact about triangles? That the three interior angles will always add up to 180 degrees, right? So what would happen if I want to add all the interior angles of a pentagon? I would be trying to add these angles. I'm signaling the angles in green. This angle, this, 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 and this. But can you appreciate that adding the 5 interior angles in this pentagon, it is exactly the same as adding the 3 interior angles in each of the triangles formed here? 1, 2, and 3. Actually, the sum of the 9 interior angles that these 3 triangles have in total, it's exactly the sum of the 5 interior angles of the pentagon. Since each of these triangles produces an interior angles sum of 180 degrees, the sum of the angles of the 3 interior angles or the 3 triangles together would be actually this multiplied by 3. And so that's how we get 540 degrees, okay? The number of triangles that we form by drawing diagonals from one common vertex in a polygon is exactly the number of sides take away 2. You can see, for example, in a quadrilateral, from one vertex, we can draw a diagonal and we split in 2 triangles. Since each triangle has a sum of 180 degrees for the interior angles, okay, in a quadrilateral, the total sum of the 4 interior angles will always be 2 times 180 degrees, and so on. Well, you see that in these figures, all the polygons that are drawn there look like they are regular or symmetrical, right? Yeah, but this formula doesn't depend on whether the polygons are symmetrical or not. It doesn't matter if the polygons are not symmetrical or regular. They could have any shape. That is to say, they could have different lengths for their sides, and they could have different angles measures. But still, this formula always holds true. So now, in case the polygon for which we calculate the sum of the interior angles is a regular or symmetrical polygon, then it's easy if we divide this formula by the number of angles, which is the same as the number of vertices, which is the same as the number of sides, that is n, then what is this? This is simply the measure of the common interior angle. For example, if it is a regular pentagon, all the interior angles of the regular pentagon will be the same. So how do we find that? Just calculate in the formula this value, which is the total sum, and then divide it by 5. And so by dividing this by 5, we get that in this particular case, each of these angles, for example, would be 108 degrees, right? Yeah, you divide 540 by 5, you get that. So, there are questions that you can see where you have to make use of these formulas. Take a look at this. 2 sides of a regular pentagon are extended as shown in the figure above. What's the value of x? Okay, I leave it up to you to think it for a moment. Okay, several of you actually got it right. Let's see how to get to the answer here, okay? It says there is a regular pentagon in the first place. So a regular pentagon, right? What does it mean? It means that all the sides of the pentagon are the same length and all the interior angles of the pentagon have the same measure. Okay, so because all these angles have the same measure, we can calculate what is the common measure for these interior angles of the regular pentagon. We just mentioned that a moment ago, right? We said that since we obtain 540 as the sum, 540 degrees, if you divide this by 5, you just get this, 508. So this would be the measure for each of the interior angles. Okay, so what happens if this is 108 degrees and this is also 108 degrees? Since here, this angle represents an exterior angle in this vertex of the triangle indicated here, and at the same time, this angle is the exterior angle of this corresponding vertex. At the same time, they are exterior angles, and because of that, you know that this measure can be easily calculated. It's the difference with 180 degrees. So here you have 72 degrees and also 72 degrees. So you would be having an isosceles. So it's easy to see that x plus 72 times 2, that is 144, equals 180 degrees. So x equals 36. Okay? That's the answer to the question. Okay, let's see one more example and some more properties. Now let's talk about triangles indeed. Well, there is one first property is very important for triangles. It's about the theorem of existence of a triangle. You may consider that a triangle can have like an arbitrary form and measure for the sides, but that is not completely true. You cannot just make one triangle with any three line segments whatsoever. For example, say that you pick one segment of one length or 1 unit length. Here, another segment of just 1 unit of length, and another segment 10 units long. Can you actually make a closed figure using these three segments? Impossible. It would look something like this. So these three segments don't form a triangle. The same would happen if you had three segments, one of 5, another of 5, and a third of 10. You would, have just a straight line. So what is going on? If you want to have any triangle, there has to be a relationship between or among the lengths of the three sides. Any of the sides can never exceed actually the combined length of the other two. In other words, in this triangle, C has to be always less than the sum of A plus B. At the same time, A has to be less than the sum of B plus C, and B has to be less than the sum of A and C. If you try to connect these three inequalities that determine the relationship among the lengths of the sides of a triangle, you could summarize by saying this. For any of the three sides, there is like a binding condition for the lengths. Any side has to be less than the sum of the other two and greater than the positive difference than the other two. Say, for example, that they tell me that this is 7 and this is, let's say, 4. What would be possible lengths for this side. Okay, if we use a formula, we could say that B has to be less than 7 plus 4 and greater than the positive difference, that is to say 7 minus 4. So B is between 11 and 3. These are the possible values for the length of side B. Sometimes questions in the SAT will tell you that the lengths of the sides have to be integer values. Okay, be careful about that. Let's see a sample question here. In triangle ABC, AB has a length of 3 and BC has a length of 4. How many integer values are possible for the length of AC? Okay, you can try. Okay, so what's the answer? Try to visualize, even if there is no diagram here, try to visualize the situation. You have a triangle, something like this, perhaps, right? Just to know or understand what is going on. Here you have 3, BC is 4, so this is unknown. And you need to estimate how many integer values exist for this length. So let's call actually AC, it has a length of X, okay? So according to the theorem of existence of a triangle, X has to be less than the sum of the other two sides and greater than the positive difference of the other two, okay? So X must be between 7 and 1. But X is defined as an integer because we are looking only for integer values of X. Take a look. How many values exist between 1 and 7 that are integers? 2, 3, 4, 5, 6. Can we consider 1 and 7? No. Take a look at this symbol. It's just less than. It's not less than or equal to. Don't consider the ends of this double inequality, okay? You cannot have a side of just 1 because if it is 1, it would violate the principle and it would look a lot like this, in which the sum of two sides equal the length of the third. That cannot be a triangle either. Okay, so that's why how many values are there? 5. That's the answer to the question. Okay? Careful about that. All right, please remember you're welcome to ask questions if you need to clarify anything, something not clear, as we move through the example questions. Let's see some more examples. But let's remember that in triangles, there are some special terms that appear from time to time in questions. For example, isosceles and equilateral. What is isosceles? Well, isosceles, anyone remembers? Here, right? Two sides of equal length. But not only that, also the angles opposite those sides are equal, okay? For example, this triangle. But an equilateral triangle is the regular polygon of 3 sides. That is 3 equal lengths and 3 equal interior angles, each of 60 degrees. Okay, so let's see another example question. It's a really good question. Need to be careful with this question. When they tell you that one of the angles has a measure of 50 degrees, which angles are they indicating? Okay, an isosceles triangle is a triangle that has 2 equal angles and 2 equal lengths, right? But think about this. It says one of the angles. The expression one of the angles doesn't make reference to a particular angle. So it could be one of the angles that are equal, or it could be the third angle that is not equal to the other two. So we have to put ourselves in the two scenarios, okay? We need to consider two possible scenarios. Let's imagine that 50 degrees is the measure of the angle different from the other two. So here it would be like this. And because the other two have to add up together with 50, 180, the sum of these two other would be 130. So each of these would have to be 65 degrees. That is one possible scenario. Another scenario would be the scenario in which 50 degrees is the common measure of the two equal angles in this isosceles triangle. In other words, that this is 50 and this is also 50. And if that's true, since the combined measure is 100 degrees, this would have to be an angle of 80 degrees because the sum is always constant, is always 180 degrees for the three interior angles. Since the question tells you what is the degree measure of the greatest possible angle in the triangle, in this case, for example, what is the greatest possible angle? The greatest is 65, right? But in this one, what is the greatest possible angle? Is 80. So what's actually in all scenarios possible? What is the greatest possible angle? Okay, we need to consider this one. So the correct answer choice would be 80 degrees. All right. Well, let's continue. Let's see this question here. You can practice this one. Here you can combine what you have learned about triangles, the property of the sum of the interior angles, also the exterior angle, and whatever else you may remember about triangles. Don't forget about any description given in the text, not only focus on the diagram, okay? Read everything. Try to do this one. Okay, so what do we do here? Take a look. This, according to the statement in the question, says that the triangle ABC is equilateral. What does it mean equilateral? Well, each interior angle is 60 degrees. This one is 60 degrees, this is 60 degrees, and this is 60 degrees. So take a look that in this sum, this is 60. We already have this. This is also 60 degrees. And then we have K plus L plus M plus N, right? But something interesting in particular about these two pairs of angles. What about these two angles? What must be their combined measure? And what about these two other angles? What must be their combined measure as well? Anyone? What should be the sum of K plus L, for example? What happens if you have two angles around the same side of one point over a line segment? For example, if I have angle X and angle Y, what is particular about these two angles? Yes, good, Luciana. The sum of X plus Y is 180 degrees because this is the measure of a flat angle, 180 degrees. So these two combine form 180 degrees. And so do these two. So this sum here should be 180 and this another 180 degrees. So you have these two, 360, and plus this and this, which is 120, what we have? Okay, we have 480 degrees. The answer to the question. All right? That would be the value to input manually in this question. Okay. Let's see more examples. Now, remember some properties about right triangles. When we talk about right triangles, well, the expression right triangle makes reference that it's a triangle that has a right angle or a 90-degree angle, right? Like the corner of a square, right? Okay, the terms they use in the SAT to refer to the sides of a right triangle, the shorter sides, this and this, are called the legs. Why legs? Is it some kind of animal? Well, I don't know why. This is the traditional term that has been used in English for a long time. What's the Spanish equivalent of this? We say something very different, right? That has nothing to do with the concept of leg. Yeah, we say cateto in Spanish. Yeah. And this one is more familiar. Hypotenuse is, of course, this longer side. Remember, the hypotenuse is the side that is always opposite the right angle. Okay? It's the longer side, by the way. And there is a universal relationship among the three lengths of the sides of a right triangle, which is the Pythagorean theorem. The sums of the squares of the lengths of the legs equals the square of the length of the hypotenuse. That's it. Say Pythagoras, right? Okay. Well, let's see one example. Try, please, question 4. Okay, so how do we calculate the height of the rectangle? Take a look. You understand that, you know, when you draw the diagonal of a rectangle, since a rectangle only has right angles, here, here, and here, so this diagonal divides the rectangle into identical right triangles. In this right triangle, number 2, for example, we have the hypotenuse would be 20 in length, and since the base of the rectangle is double the length of the height, so if the height is x, then this base would be 2x. And how are these three lengths, the length of the two sides of the rectangle and the length of the diagonal, related? How are they related to one another? By the Pythagorean theorem, right? If we think about this triangle, I will draw it apart, 20x and 2x. So it must be true that the sum of the squares of the lengths of the legs, that is x squared plus 2x squared, equals 20 squared, which is actually 400, right? So can we solve this for x easily, right? Because we have seen how to solve quadratic equations. This is 4x squared equals 400. And thus 5x squared equals 400. We can isolate. Remember, 100 divided by 5 is 20. So here, 80, right? And x squared equals 80. Therefore, x equals, okay, be careful here, okay, with your algebra. It's true that x should be, you know, plus or minus the square root of 80. But since we're talking about distances, lengths of line segments, we can never consider negative values here, okay? So forget about this second possibility. No, it's just the positive square root of 80. Okay, remember that if you factor this out, as you know, using the properties of exponents, 16 times 5, or 2 up to 4 times 5. So you can see easily that if you separate this like this, square root of 2 up to 4 times the square root of 5, then this one can be expressed as just an integer value. So this would be 2 squared, right? Or 4 times the square root of 5. And this would be the correct answer. That's the length of the height. Well, let's see more examples. Now, in questions where right triangles are involved, there are especially two triangles that have a special proportions or special relationships for the lengths of their corresponding sides. We have, for example, the right triangle that can be drawn when you, for example, have this, a square. And if in a square you draw the diagonal of a square, okay, you form exactly this special triangle, which is a triangle that has two equal angles of 45 degrees each and one right angle. And so there is this connection between the length of the common leg, x, and the length of the hypotenuse. It is the common length multiplied by square root of 2. There is another special triangle that has two angles of 60 and 30 degrees, and of course a right angle. And the proportion, that exists among the three sides, is like this. It's like 1k k times the square root of 3 and 2k. That is to say, the shorter leg is like k or x. This is the longer leg, and this is the hypotenuse. And it's interesting, the shorter leg will always be the segment that is opposite to the angle of 30 degrees. The longer leg will be opposite to the angle of 60 degrees, and of course, the hypotenuse is the longest side. The instant connection is here, right? Between the shorter leg and the hypotenuse and the longer leg, there is this connection. The hypotenuse twice the shorter leg, and the longer leg is just multiplying the shorter leg by the square root of 3. So if you memorize these proportions, you can do questions like this. For example, here, what's the area of triangle ACB shown above? They give you this triangle. It's a right triangle, and it's the isosceles right triangle because it has two angles of 45 degrees each. You just are given the length of the hypotenuse. So what's the area? Okay, you can try. Okay, guys, this is a really direct question. How do we handle this? The idea is that you remember the proportion of the special isosceles right triangle, okay? Since this is x, and this is also x, and this must be x multiplied by the square root of 2. Okay, so the first important thing in our business is to calculate x. Why? Because to calculate the area of an isosceles right triangle, you can actually say, okay, what about this is the base And since this side AC is perpendicular to BC and it's exactly drawn from the opposite vertex, so this completely fits the definition of the corresponding height. So base times height over 2. In other words, the area would be x times x, or x squared, divided by 2. So all we have to do is just calculate x and then substitute to calculate the area. So what is x? If x square root of 2 equals 4, then x equals 4 over the square root of 2. Since we are using x squared, forget about rationalizing this. It will be faster if you simply say that x squared is simply this, or 16 over 2, which is actually 8. And all you need is this divided by 2. So actually the area of the triangle will be 8 divided by 2, or 4. So the correct answer is option C. Okay? Well then, let's continue. Let's see more examples. Question 6. You can try this one on your own first. Okay, let's see the solution to example 6. In the figure above, this triangle ABD, AD equals DC, angle B equals 30 degrees, and segment AB equals 10. What is the ratio of AC to CB? Okay, here, first of all, notice that in the SAT, the notation they use to refer to line segments is always two capital letters referring to the two endpoints. So AD means this segment here, right? But at the same time, this notation can not only refer to the segment itself, but also to the length of this segment. So saying, for example, AD equals X, that means that X is the length of the segment AD. Okay, so we are saying that AB equals 10. Obviously, here is 10. You don't need to actually have this explicitly because the diagrams informs you so. But then we have that this angle is 30 degrees. Segments AD and DC are the same. That means this is X and this is also X. Okay? What else? Well, we need to find a ratio, AC to CB. In other words, we need to find this quotient. What is this? Can we solve this? Okay, let's see. First of all, something interesting is that since triangle ADC, the one with the sides AD and DC, is an isosceles right triangle, so clearly this segment here must be x times the square root of 2. It's an isosceles right triangle. At the same time, this is a 45 and 45-degree angle. And because triangle ABD has one interior angle of 30, that means that the other interior angle that is not the right angle that is here, this angle here must be a 60-degree angle. So how do we find AC to CB? What is AC? Take a look. AC is this part, is this side here that we define as x multiplied by the square root of 2, right? We can say that in terms of x, AC equals, is the hypotenuse, so it's x times the square root of 2. What about CB. CB is this side. Can we find a connection between CB and X? Well, think about that for a moment. If this is X and the hypotenuse is 10 in triangle ABD, it follows, because of the properties of the special triangle with angles of 60 and 30 degrees, that this must be half of the hypotenuse, that is to say 5. But if this is 5, then what happens? Well, obviously, the connection between the shorter length or the shorter leg and the longer leg, that is all of this. This is the longer leg. What should be the longer leg in terms of X? Well, according to the properties of this triangle, 60, 30, and right angle, if this is X, this should be X times the square root of 3. So what is the length of DB? DB would be actually 5 times the square root of 3. Okay, good. Now, what about CB? CB plus X is DB, that is to say 5 times the square root of 3. So according to this equality, the length of this side, the segment CB, should be 5 times the square root of 3, take away X. Okay? So now, if we substitute this expression here, so we are forming this quotient, AC, which we know is X times the square root of 2, or we can now write it directly, right? Because it's 5 times the square root of 2, okay? And divided by CB, which is 5 times the square root of 3 minus 5. Well, we can clearly see that 5 can be factored up and down because we have this. And we have, sorry, square root of 2 is missing. Square root of 2 divided by square root of 3, take away 1. It corresponds to option A. Okay, that's it. Well, let's continue. Let's now talk about another property that polygons and particularly triangles have. This is the property of similar or proportional triangles. When do we say that two triangles are similar or proportional? Well, when the two triangles have exactly the same three angles. If they have the same angle measures, then their sides are proportional. That is to say, the sides that are opposite to the same angles, okay, in the two different triangles, they follow a common proportion. You can see here in these two triangles that we have drawn, okay, it's two right triangles, so they have this common angle, of course. Also, this is another common angle, and of course, they share this angle. So they have exactly the same three angles, right? It follows then that the corresponding sides that are opposite to the same angles must be proportional. AB, that is to say this longer side, is to BD here as DE, or AC is to DE. What is AC? This proportional to this. And so BE, which is, or BC, this long hypotenuse is proportional to this short hypotenuse. So they have the same proportion for the 3 pairs of corresponding sides. And which sides are corresponding? Remember, the sides that are opposite to the same angles. So using this, you can see questions like this, no problem. Be careful when they give you questions like this. For example, here there is a diagram, but it's accompanied by some note. It says figure not drawn to scale. So don't try to estimate the length of the segments in the figure just visually, because what you know, it appears, to plain sight is not exactly what you can calculate using the property of similar triangles. So when they tell you figure not drawn to scale, imagine that it is a way that the exam makers are recognizing that the figure is distorted, okay, or deformed purposefully. Okay, be careful. Don't make many inferences or conclusions based only on the diagram. Apply the properties, do your calculations in order to get to the correct answer. So you can try to solve this part 1. Okay, so they tell me in triangle ABC above, segment D is parallel to AC, AD equals 2, DB equals 3, and DE equals 6. What is the length of AC? That is to say this one. Well, notice that the fact that they tell you that DE is parallel to AC, it means that this angle here, alpha, must be the same as this angle here. And also, this angle here, beta, must be the same angle here, beta. This is applying the properties of parallel lines when they are intersected by a third line that is not parallel to them. So what can we see? Because of just this property of the parallel lines and the angles in the intersection of parallel lines with a third line, we can see that the two triangles in the figure share two angles. Two interior angles are the same. And the third interior angle, it's actually shared by the two triangles at the same time. Let's say angle gamma, okay? So these triangles are proportional, and we can formulate proportions between the lengths of their corresponding sides. So this proportion, that is to say, side AB, that is the side opposite to this angle beta in the big triangle, is to DB, the same side in the small triangle opposite to angle beta. Okay, this relationship or this ratio must be the same as AC divided by DE. The two corresponding sides opposite to angle gamma. So what can we say? Well, AB, we know because it is actually the sum of these two, 2 and 3. So this is 5, that is to say AB. DB is just 3. Then AC is what we want to find out. And DE, we have 6 here. So based on this, we can simplify and then cross product. AC would be 2 times 5, 10. That's the answer to the question. Okay, so that's a way you can work with proportional or similar triangles. Why is like risky to not pay attention to this notice? Because you may say, oh, if this is 6, maybe this is like, I don't know, it looks like 8 or something. This one here. Remember, this figure is completely deformed. Why? Because here you have this segment that is 3 units, but here this looks almost, actually it looks shorter, but it is 6. So actually the lengths don't correspond with the apparent length, right? The true lengths don't correspond to the proportions of the figure. So be careful not to make inferences from these apparent proportions. You need to follow the exact proportions based on the property we just mentioned here. That is to say, the ratios of the corresponding sides that are opposite to the same angles. Okay? For example, here are the opposite to this, let's call it angle alpha. But here, if this is angle beta, this is also angle beta. So here is the proportion of those opposite to beta. And here is the proportion or the ratio of those opposite to 90 degrees, to the right angle. Okay, that's the point. Okay, so let's keep going. There is a part 2 to this question. Same figure, okay, but now you see this question here. So how do we do this question here? Okay, here is what's the ratio of the area of the triangle BDE, that is a small triangle, to the area of the triangle BAC. Now, you perhaps would try to, how to say, find a way to calculate the areas and then calculate the quotient, but that would be too long. So be careful not to fall for that trap. There is an interesting property of the similar triangles. So if we know that the corresponding sides of two triangles, let's, here draw two triangles that are similar, okay? And they have their sides, but the angles are the same, alpha, beta, gamma. Alpha, beta, and gamma. So they are similar triangles. Let's say that you know that here you have L1 and L2. You know that the ratio of their corresponding sides is a known value. Let's say K. This similarity gives us the possibility to estimate immediately what is the relationship between their areas. Let's say that the area of this triangle is A1 and the area of this is A2. So A1 over A2 will always be the square of this ratio here, K squared. Okay, so if you know the ratio of the corresponding sides of two similar polygons, the ratio of their areas will be the square of the ratio of their corresponding sides or lengths. Okay, only applicable to similar figures. Okay, proportional figures. So using this idea, and of course, this works vice versa. For example, if you know the ratio of the areas of two proportional polygons, what would be the corresponding ratio of their corresponding sides? That is to say, the sides opposite to the same angles. Okay, simply take the square root of the ratio of the areas and you will get the ratio of the corresponding lengths. That's it. So take a look at this. What is the ratio, the common proportion between two corresponding sides between the two triangles? For example, we notice that what is this length here? This is 5. And what is this length in the shorter or smaller triangle? 3. So we know, so to say that L1 is to L2, okay? Let's say that this is L1 and this is L2. So L1 is to L2 as 3 is to 5 because we are checking the proportion but considering above the smaller triangle, this one, BDE. And then below is the bigger triangle. Since we want to find the ratio of the area of the smaller triangle to the bigger triangle, then simply this ratio, or area 1 to area 2, would be like this. It would be this proportion, but squared. So it's simply or 9/25. And this corresponds to option D. So that's how you can solve questions where they ask you to find the ratio of the areas of two proportional figures or similar figures. And remember the principle of similarity. If there is a common proportion between corresponding sides of two polygons, right? In triangles, those corresponding sides must be the sides that are opposite the same angles. Now, it's time to talk about, the measures of angles, radians, okay? Radians is a unit that we measure angles by, similar to sexagesimal degrees. There is just an equivalence. Pi radians equal 180 degrees. So whenever you want to calculate the measure of an angle in radians, just use the conversion rate, such as this, if you want to move from degrees to radians, or this one here, if you want to move from radians to degrees. For example, what is 45 degrees in radians? Multiply the measuring degrees by the corresponding conversion rate. Remember, we worked a lesson about rates and rate conversions. Just multiply it, so degrees with degrees will cancel, but you get the measuring radians is the result of multiplying 45 times P over 180. So you get pi over 4 radians. And what is a measure in radians? For example, 3 pi over 2, this here, in degrees, in sexagesimal degrees. So just convert by the inverted rate, this one, and you will get this. So remember, this measure, this angle, which is 180 degrees, is also pi. So the a complete loop or a complete turn of 360 degrees, this is equivalent to 2 pi radians, okay? This is pi radians, and this is 2 pi radians. And that's it. Let's see an example. In the XY plane above, line M passes through the origin and has a slope of the square root of 3. If point A lies on line M and point B lies on the x-axis as shown, what's the measure in radians of angle AOB? So which angle we want to measure? This one. First, let's find the measure in degrees. How come? If this has a slope of square root of 3, remember what is the slope? Is the rise over the run. So what is, if this is square root of 3 over 1, this means for a run of 1, you get a rise of a square root of 3. So let's do this. Here is the run, 1. And here is the rise, square root of 3. That's it. So what do we have here? Since this is perpendicular, okay, to the x-axis, we have actually a little right triangle that has one leg of square root of 3 and another leg of 1 unit of length. So does this ring a bell? Does this correspond to any of the special triangles we've seen today? What happens in this triangle? 30, 60, and 90. This is x. This is x times the square root of 3. So what's going on here? If we rotate this a bit, we'll see the pattern, right? If this is x and this is x times the square root of 3, for example, x could be 1, and so the vertical leg would be square root of 3 simply. This is 60 degrees. So this measure is 60 degrees. That's it. That's what we can conclude about the coordinates of point A, right? Yeah, another approach would be to say, oh, what is the equation of the line? It passes through the origin and the slope is the square root of 3. So you say, okay, the equation is y equals the square root of 3 times x plus the y-intercept since it passes through the origin plus 0. So just this. And from this to say, okay, when x equals 1, y equals the square root of 3. The same. You will get to the same conclusion. The important thing is that at some point, you will get to the measure of the angle AOB is actually 60 degrees. So let's do the conversion. 60 degrees times pi radians over 180 degrees, our conversion factor. So simplify, and you get pi over 3 radians. And that's it. Option D. Okay, let's move on. With this, we now need to talk about the properties of circles. Well, for circles, it's all about formula, right? For example, in circles, you have the area of a circle. Okay, needless to say that you know what the elements of a circle are. If you have a circle like this, there is a reference point called the center of the circle, and between the center of the circle and each point on the border of the circle, okay, this segment is called a radius, right? So considering this, the area inside the circle is pi multiplied by the square of the radius. Remember, pi is this irrational number, 3.14159 and so on. Okay, in most SAT questions, you just need to deal with pi like a letter, okay? You express your results in terms of pi. If you ever need to calculate an approximate value for a result including pi, just use this, okay? As an approximation, 3.1 will do, no problem. Forget about 3.1416, okay? Too much. The circumference, what is the circumference? Is the length of the border of the circle. 2 pi or 2 times pi times the radius. What is an arc? Well, an arc is actually a portion of the circumference between 2 points on the border. Say, for example, this is point A and this is point B. So what is an arc? For example, this portion of the circumference between points A and B. It's possible this, or it's possible the other way around. For example, this. In both cases, you have an arc that ends in A and finishes in B. Obviously, there are two possible lengths. So an arc can be, estimated its length. How? Using this formula. This is the measure of the central angle, that comes from the two radii, okay, from the endpoints of the arc. So what is this? This is angle theta. Okay, so that's the angle in this formula. If that central angle, which is the measure of the arc, but in degrees, divide by 360 and multiply by the circumference. So this is like giving you a proportion, right? A proportion of what part of the whole circumference represents the length of the arc. This fraction sometimes you can estimate simply by visual inspection. Imagine, for example, they tell you this. There is an equilateral triangle inscribed in a circle. So you have something like this. So you understand that because of the symmetry of the figure, the arcs that are formed between all the vertices of the triangle will have to be the same length. For example, here, if they tell you what is the least length for this arc between vertices A and B, obviously that length has to be 1/3 of the whole circumference because of the symmetry. So sometimes this fraction here, you can just estimate by checking the figure or the drawing visually, okay? Now, if you want to work with radians, if you have the measure of an arc, the angle, this angle here in radians, just multiply that by the radius, and that's the length of the arc. So it's very convenient. Then, what is the area of a sector? Imagine that we have this closed figure. The two radii from the center of the circle to the endpoints of an arc and the arc itself. They form this closed figure, right? It has an area. It's like the slice of a pizza. So that is a sector of a circle. And it has an area that is proportional to the measure of the central angle. So again, this factor, theta over 360 multiplied by the area of the circle. But if you have the central angle of the arc in radians, not in degrees, then there is this simpler formula. 1/2 of the square of the radius multiplied by the angle in radians. Okay, that's it. The idea is that, you know, this arc, what is the measure of this arc in degrees? The measure is always the measure of the corresponding central angle formed by the two radii that comes from the endpoints. So we say that this central angle measures 60 degrees and also the arc AB measures 60 degrees. But that is a measure in degrees. If they ask you to calculate the length, you know to use this formula. Okay? The length of the arc is different. There are many kinds of angles in a circle, but in the SAT, you will only have to remember the definition for two of them. This one, which is called a central angle, remember, two radii converging in the center of a circle. That is a central angle. What is an inscribed angle? Okay, when you have a circle and you have a segment that connects 2 points on the border of the circle, for example, X and Y. What is this segment? They usually call this a chord. Okay, so if you have two chords in a circle and they have a common endpoint, that endpoint is called an inscribed angle. Take a look. So you have, for example, point X, point Y, and point Z. The two chords, XY and XZ, form an angle here. This is called an inscribed angle. But now take a look. If you know the measure of this arc here, from the endpoints of an arc, you draw an inscribed angle, that inscribed angle will always be half the measure of the corresponding arc, the measure of the arc. If the arc was 60 degrees, then the inscribed angle is 30 degrees. And it doesn't matter which inscribed angle. For example, I can draw any other inscribed angle from the endpoints of this of this arc, for example, here. This also 30 degrees, same measure, okay? And so would be here. Let's see this one. This is also 30 degrees, okay? Let's see an example now of the property of the inscribed angle. Imagine that you have an arc, this arc here, that is a semicircle. So this is an arc of 180 degrees, right? A semicircle. If from the endpoints of this arc you draw an inscribed angle, because of the property of the inscribed angle, this angle has to be half of 180, that is to say 90 degrees, okay? So inscribed angles in a semicircle are always 90 degrees. It doesn't matter which or how you draw it. For example, this one here will also be a right angle. The concept of a line tangent to the circle, okay, it's easy to see that if a line touches a circle in just one point, in that contact point or tangency point, if you draw a radius, this radius is perpendicular to that line, okay? Oh, sorry about that. Let's continue. And we have some more information here. This is the general equation of a circle in the XY plane. Yeah, there are some questions in the SAT about circles in the system of coordinates. So if you have a circle that has a center in the point HQ or HK, then the corresponding equation to the circle is this, okay? X minus h squared plus y minus k squared equals the radius square. The r is the length of the radius. So that's a general equation that you can use to solve questions. Take a look. Example 1. In the figure above, the outer circle's radius is twice as long as the inner circle's. What is the ratio of the area of the shaded region to the area of the unshaded region? There is a long way and a fast way to solve this. What would be the long way? Okay, the long way would be to first try to calculate the area of each and then calculate the ratio. But that is a long way. Let's imagine that we have this center, common center for the two circles. What is this? This radius. Let's say it's X. Since here we are supposed to find the ratio of one area to the other, don't make the mistake that start using variables. Take a look. The 4 answer choices are just numbers. So that means that this should work with any two circles that comply with the proportions presented. So you pick the values that are easier to work with. Don't use variables. For example, I can say that this radius is 1. So what would be the radius of the outer circle? Since it's twice as long, I say that this radius will be 2 simply, because it's twice as long. So what would be the ratio of the area of the shaded region? What is the area of the shaded region? It's this. Is the area of the bigger circle take away the area of the inner circle. So you have pi times 2 squared take away pi 1 squared. We are using the formula of the area of the circle. That is the shaded region. So this is simply what? 4 pi minus pi, 3 pi. And what is the area of the inner circle? Obviously, it is this one, pi times 1 squared. So what is the ratio? Shaded region to unshaded region. Shaded region over unshaded region, 3, and that's it. Okay, that would be the fast way to do it without variables. This is always a smart choice because you avoid complicating yourself with variables and expressing the operations. Just use simple values. Yeah, it works. This kind of assumption works whenever you have only numerical values in the answer choices. Now, this one is a little bit more challenging. What's the area of the shaded region in the figure above? Now, take a look at this. You have a circle, the center supposed to be C, right? And you have the radius 2. You have here a central angle, 45, and you have this shaded region. The shaded region could be defined as a difference of two areas. Which two areas? Take a look. You can understand this shape as a subtraction. This one, take away the triangle, right? You can see this shaded region as a subtraction of two areas. What is this? This is a sector of a circle. We have a formula for that. And what is this? Well, this is what? This is a triangle, right? And it is an isosceles triangle, by the way. Why? Because this is also 2, because it's also a radius. So how can we solve this? The sector of a circle here, right? You can calculate by using the formula. What is the formula? It's 45 over 360, central angle over 360 times pi times 2 square. Okay, of course, this is, you know, the same as 4 times 90, so you can simplify this. You just get 1 over 8, right? Or pi, 4 pi over 8. So it's actually just pi over 2. That's this sector of a circle. How about the triangle? How can we calculate this triangle? Do you see a way to do it? It's an isosceles triangle. So you perhaps may say, oh, but how can I find, for example, the height here and this length here? It's not so easy, but use the properties of special triangles. What about drawing the height to this horizontal radius, this here? This is the height relative to this side of length 2. Can you calculate the height? Yes, because if you draw this red side, if you have 45 here, this is also 45, and you have the isosceles right triangle, right? According to the definition, if the hypotenuse in this red triangle is 2, then the height should be the square root of 2. That is to say, a number that multiplied by the square root of 2 would be also 2, right? This one should be h multiplied by the square root of 2, according to the properties of the isosceles right triangle. So h is square root of 2. Now that we have the height for triangle ABC, it's simply a matter of multiplying base times height over 2. So what is the area? The area of triangle ABC would be 2 times the square root of 2 divided by 2. In other words, this is the area of the triangle. So now it's just a subtraction, right? This, take away this, it should be option D. Okay, so that's how you can combine the theory of circles with the theory of special triangles. Sometimes questions happen. Let's see a couple of examples to finish. Okay, you can try this one. Remember that when we finish this, you'll have 25 minutes to do the next quiz, okay? So get ready for it. Just let me, as you continue doing this, just let me remind you that in all your homework documents, I've already created a table where to fill the answers, second column, remember, only second column, the answer for today's quiz number 5, okay? For all of you. Of course, I will, um, let you work on this on the last 25 minutes. It's up to you. It's not mandatory, but if you finish this, there is a score for this. Okay. Okay, so let's continue. Remember that here, for example, in this question says a circle with diameter of 10 is shown in the figure above. Is angle AOB equals 120 degrees. What's the length of minor arc? When you see this expression minor arc AB, it refers to the shortest path between the two endpoints. In other words, the arc that goes from A to B following this path, which is obviously the shortest, right? Okay. Okay, here you need to be really clever, really clever. Why? Think about it. This is just 120 degrees. It's the third part of a whole loop. So it follows that this arc should have a length which is just 1/3 of the whole circumference. Since the diameter is 10, that is to say that each radius is 5. So what is the circumference? It's this 10 pi. And what is the third part of the circumference? As it should correspond to this arc. Simply 10 pi over 3. And that's it. Okay, one more. In the figure above, angle ACB is inscribed in circle O. What's the measure of angle ACB? It should be like immediate, right? It should be immediate. Which one do you think it is the answer? ACB. This is an inscribed angle. And this inscribed angle should be half the measure of this arc. What is the measure of this arc in degrees? Well, obviously, is the measure of its corresponding central angle, which is this. So if this is the central angle is a right angle, the measure in degrees of arc AB is 90 degrees. And the measure of any inscribed angle from the endpoints of this arc should always be half. That is to say, 45 degrees. So answer C. Finally, we get to example 5. The equation of a circle in the xy plane is given above. What are the coordinates of the center of the circle? Aha. Do you remember that the equation of a circle is this, right? X minus h squared plus y minus k squared equals the square of the radius, where h and k is actually the coordinates of the center of the circle. So what can you do in order to find h and k? Obviously, what you can do is transform this equation in this form. In order to do that, you have to complete squares, right? Complete the square trinomials and then factor them. And so that you can find not only this form, but also what is the radius. Do you feel confident about this? How would you do it? Okay, let's do it all together, okay? Remember, you have these two. From this, I will complete the trinomial, the square trinomial. This is supposed to be twice the product of the first and the second term. So this is actually x squared minus 2 times 2 times x. And so the second term should be 2, right? The square of 2 here. But if I'm adding the square of 2, I need to take away the square of 2. So that's it. Similarly, for this part, I have y squared plus 2y. So this should be, right, 2 times the product of the first and the second term. So this is y squared plus 2 times 1 times, you know, y. And so here it should be plus 1 squared. But if I'm adding 1 squared, I need to subtract 1 squared. And so this sum equals 31. Let's now factor this part, and we have x minus 2 squared minus 4, this part, plus y plus 1 squared minus 1 equals 31. And so x minus 2 squared plus y plus 1 squared equals 31 plus 5, or 36, which equals 6 squared. And now take a look. You need to mark the answer. Be careful. Be careful not to do this. Say, oh, 2 and 1. No. Remember, it has to be in this form. So we have x minus 2. Okay, good. We have the minus. But since here we need a minus, we can put a double negative sign. Plus y minus minus 1 squared. And this is 6 squared. So now we can identify our h and k. This one is h. This one here is k. So the correct answer is 2, negative 1.